Hello people, Zach here again today, and this is going to be a short video talking about the nature of particles and quantum mechanics. So I guess we're just going to go ahead and jump right into this. Suppose that we're trying to model a particular system, right? And what we have for this system is we have a box, and there's a bunch of gas particles that are kind of flying around, little molecules or atoms or whatever. We don't really care what it is. But we have a speaker out here. And our speaker emits a sound, which then, of course, causes this wall to vibrate, which imparts a force on the particles. And this causes a wave to propagate outwards. Maybe it bounces around the box, goes in all different kinds of directions. And we're trying to model this particular system of this sound propagating through this, this box. Now, our first intuition behind how we might model this would be to consider to model all of the individual particles within the box. So maybe we might consider, well, what does a particle have? Well, maybe a particle has a velocity, we're going to call that a v, and of course a mass. And if it has a mass and a velocity, that means it has a momentum, and we can use that momentum to impart a force on another particle. So then we might say, okay, well, we can model particle collisions, like what happens like when these two particles are heading in certain directions. Like we might consider the point at which they impact and reflect the vectors over the top of that particular line. Like there's different ways we can model this. There's only one big problem with trying to model this system in this particular way, which is that if you're trying to model something in an accurate way, there's way too many particles. So to put it in perspective, if you've ever dabbled with chemistry at all, you probably know what a mole is. A mole is an Avogadro's number of atoms. Particularly, it's the number of atoms in 12 grams of carbon-12, which is 6.022 times 10 to the 23. And to put in perspective again, just how big this number is, that's 6.022. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 19, 20, 21, 22, 23. It is that many particles. And bear in mind, this is just for 1 gram. So if you're trying to simulate multiple grams of whatever gas that you have, forget it. It ain't happening. There ain't no computer on Earth that has, that's going to be able to simulate this. So how do we actually do this problem? Well, and reality is that we don't do it in that way. What we do is that we either use significantly fewer particles, a lower resolution, or what we'll do is we'll create like a grid, like data structure. And each cell of this grid will have certain properties. Like maybe it has, 3 particles in it, and this one has 2, and this one also has, or like this one has 4, and this one has 2, and this one has 1, and this one has 1, and this one has 3, and this one has 1, And then from all of these different properties that we have in there, we might have certain adjacency rules. Like we might say, well, if the number of particles on the left is greater than the number of particles on the right, then we have an overall rightward flow. And so based off of the different rules that we have for adjacency between these different cells in this grid, we can determine how the fluid flows in the system. And necessarily speaking, nothing is actually moving in the system. It's just the attributes of the system that are changing. And this is kind of similar to what I talked about in one of my previous videos about the ether not having anything flowing. It's just like an image on the ether, almost like Conway's Game of Life. But that was more of a physical thing. This is just us talking about how we would simulate such a system that has so many different things going on inside of it. Now, this leads us to the next big problem that we have to consider, which is that there are different types of waves that can propagate through these systems. One of them is a linear wave. Now, a linear wave, as the name suggests, propagates along a line. As a compression wave, pretty much. So this is what sound does. Like if I were to speak here, like I open my mouth and I say something, you have a high compression right next to my mouth, and it kind of spreads out to its normal density. Then that wave will start to propagate as it goes to the right, until eventually it gets further and further away. maybe it starts to spread out. And of course, another way we can kind of think of this as well is that maybe if we had like a speaker that was sitting on a pedestal in the middle of a room, that the near where the sound is actually at, we would have a high density wave, and as it gets further away, it becomes less and less dense. It kind of attenuates, but the wave in general propagates outwards from the direction of the emission. Now, a linear wave is different from a transverse wave. Transverse wave, pretty much the only good example you can get is either like the surface of water. Like you can imagine if you had water that was like this, and you had you dropped the rock inside of it. Well, what ends up happening is that these waves will create ripples that go outwards, and they create like these outward rings that go outwards from the center. And see, the main difference is that the compression for a linear wave happens in the direction that the wave is propagating, whereas with a transverse wave, the ripples are happening perpendicular to the direction of propagation. So like with a light wave, you've probably seen this depiction before, and you're going to have to forgive me because this is a really difficult thing to draw. You'll see like a wave of light going this way, and this going this way, and part of the wave is oscillating in one direction, while the other one is oscillating in the other direction. So like your one wave is oscillating that way, and then it's that way, and then that way, and then that way, and that way. And so it might be a little bit easier to see now, but an easier way to see this as well, I think, is just to like imagine you have a plane right here, and this circle right here is what it's representing, is that you have it's actually coming straight towards you out of the paper. You can imagine that you have like an electric field that's going this way, oscillating back and forth, and a magnetic field that's going this way, oscillating back and forth. And because the fact that transverse waves actually have 2 degrees of motion as opposed to the 1 degree of motion, you can actually polarize them in one of 2 different ways. You can polarize them linearly, or you can polarize them circularly. And you're probably familiar with linear polarizers because they appear on like glasses and stuff. And basically what a linear polarizer does is you can say like, we're going to horizontally polarize the glasses, and what this does is it eliminates the vertical component of the glasses. So you only have light that's acting along this horizontal axis. And if you were to polarize light one direction horizontally and then try to put it through another polarizer that moves vertically, you'll find that no light comes through at all, which is how your liquid crystal display screens work. Now, circular polarization is a little bit different. This has to do with doing a phase shift. If you get these two, the electric and magnetic components, out of phase with each other, what ends up happening is that like it almost appears like it's wobbling, like it's going in a circle. And that's just I don't even know how I could even begin to explain that, but that's just the general idea. But it's not just this that you have to be concerned with. The other issue that you have to be concerned with is that suppose that your the absorption and emission, like with the sound right here, we weren't even really considering like the rates of absorption and emission, but with something like light, you have to consider the fact that the absorption and emission of light waves happens at discrete energy levels. And what this basically means is like, suppose you have, I'm trying to think of a good way that I can do a depiction of this. It might actually be easy to do this with just squares. So imagine that you have squares, right? And these squares always come in pairs. Your squares always come in pairs. You can never have an unpaired square. Now, what this means is that if you want to get this energy level right here to emit a wave at this energy level, you need to have both of these squares filled. And if you want to emit a wave at this energy level, you have to have all 4 of these squares filled. And if you want to, emit a wave at this energy level, you have to have all of these squares filled. You cannot just fill one square and then produce an energy wave at this level. It's not allowed. Now, this is a very crappy model for trying to explain this, but bear in mind, I'm really just trying to simplify this as much as possible. The thing is that because there are these different rules behind how different waves propagate and how different waves interact with each other, you're going to have different simulations, like different models for simulating these things. And within the realm of quantum mechanics, there's actually 3 different statistical models that we can use to model things. One of them is known as the Maxwell-Boltzmann statistical model, which is what you would normally use to simulate things that are atoms and molecules, like this room full of gas particles that you're sending sound waves through. But the other 2 ones, which are the ones that are what you see in the standard model, are the Boltzmann, or sorry, the Bose-Einstein statistical model, which is used for bosons, and the Fermi-Dirac statistical model, which is used for fermions. And literally, what a boson and a fermion is a boson is a particle, air quotes, of something that seems to abide by the Bose-Einstein statistical model, and a fermion is a particle, air quotes, that for some substance that seems to abide by the Fermi-Dirac statistical model. So whether or not it's comprised of bosons or fermions really just depends on which statistical model seems to be matching what it is that it's doing. It doesn't mean that you can actually see the individual things, because actually what is happening is that once you get down to the atomic scale, even just seeing atoms themselves is borderline almost impossible. Now, it's not actually impossible, and like we can use like X-rays crystallography or different techniques that we might be able to see individual atoms, but when it comes to seeing things that are smaller than atoms, we do not see crap. What we see is like a weird like aura that seems to be glowing around these things, and we might be able to measure certain properties, like maybe it has a particular charge, or maybe it has, whatever. But the thing is that we're trying to model this thing right here, and we don't really know how many particles in it. Well, the very thing that we could do is we can still do this type of simulation where we're not actually simulating the individual particles. We're just simulating like statistically like how it works on a larger scale, and that's just fine. Now, as I said, in quantum mechanics, you have 2 different types of particles, and there's no overlap between these at all. One is the bosons, which are your abide by your Bose-Einstein statistical model, and your fermions, which abide by your Fermi-Dirac statistical model. Any particle is going to abide by one of these. Like your bosons normally include your things like your photons, and your fermions will include your things like your electrons. So these work in 2 different ways. Now, here's something else to consider, right? You know what a Bose-Einstein condensate is, right? It's a particular state of matter. The thing is that a Bose-Einstein condensate is actually, as the name implies, abides by the Bose-Einstein statistical model, which means that it's comprised of bosons, but yet it's matter. Yet, for some reason, it appears in the same category as photons. Well, here's the thing, right? As you know, hydrogen is an atom, and an atom has nucleons in it, which are your protons or your neutrons. And of course, atoms that have the same number of protons are always the same atom. I mean, it's the same element, but if they have different neutrons, they're said to be different isotopes. And you can have multiple different isotopes of hydrogen. Like you can have protium, deuterium, and tritium, which have 1, 2, and well, they have different number of neutrons. I can't remember off the top of my head what it is exactly. But anyway, the different isotopes of hydrogen are also known as hadrons. And a hadron can actually behave as either a boson or a fermion, depending on the type of experiment involved. So if you have a hadron, oh my gosh, I call this hadrons. Your hadrons are going to be are always going to be behaving as either bosons or fermions, like never anything in between. And when they are behaving as bosons, what we call them is baryons. And when they're behaving as fermions, what we call them is mesons. So a boson-Einstein condensate actually consists of hadrons, which are baryons, which are bosons. That's why we call them a Bose-Einstein condensate. And there's other things as well, like, you know how sound up here, we know that sound is a wave propagating through a medium? Well, the quantum mechanical view of sound is that it consists of sound particles, per se, phonons, Phonons, and those phonons abide by the Bose-Einstein statistical model, which means that they are bosons. So a phonon is a boson. Now, obviously, there is no real sound particle. Like there's sound is waves propagating through a system of particles, but a phonon is not these individual particles that we were talking about before. It's a conceptually completely different thing. It's not a real physical particle. It's just a mathematical object that has a certain set of properties that we would ascribe to creating this system that we can use for predicting how the object evolves over time. So really, when they're discovering particles, what they're doing is they're looking at the system and how like the interactions behave in the system, and seeing like if it abides by a certain, set of rules, and then from that they can determine, well, if it abides by this set of rules, then it's a boson, or if it abides by this set of rules, then it's a fermion, and then they might determine from there, like, well, the different parameters that are involved in that particular thing, like maybe is it appear to be behaving as though it has spin up, or does it appear to be behaving as though it's spin down, or does it appear to be behaving as though it has this energy level, or behaving as though it has that energy level? Like these are the things that they're doing when they're discovering these different particles, and based on these different parameters, they can determine, okay, well, at this particular energy, we have this particular type of interaction that seems to be appearing, and this is reproducible. Now, these are not things that I disagree with at all. When I'm saying that these particles aren't real, that it's all waves, basically what I'm saying is that, like, it goes back to my ether idea. Like, yes, we have this system, but there's not real particles there. This is us trying to quantize something that is happening at a continuum, within a continuum. There's no discreteness to it at all. But anyway, I hope this clears some things up about what I was talking about when I talk about particles and quantum mechanics. Like I'm saying that these aren't real physical particles. These are us modeling things. But the way that things actually interact, like when you observe them in physical experiments, they behave as though they're waves. Like light experiences things like Poisson spots, or diffraction patterns, or linear and circular polarizability, which is something that like classical particles would not be capable of doing. It has wavelength shifts, like you have redshift and blue shift, which is basically like a Doppler effect, but for sound. These are all properties that are unique to being a wave. I mean, the fact, like the double slit experiment, that the fact that light can go through both slits in a particular experiment seemingly and interact with itself, that is a property of a wave. You cannot recreate that property using classical particles. And even the energy of the particle itself is defined as, E is equal to hf. Well, what is H? That's Planck's energy, Planck's constant, that's energy. F is frequency. What is frequency? Well, frequency is a number of cycles over a particular period of time. And, of course, if you had, 4 cycles in 2 seconds, you can simplify that down. Dividing it by 2, we get 2 cycles in 1 second. Or what we can do is, if we wanted to have a 1 as a numerator, we can say 1 over half. And so now we say it has half frequency, but that doesn't mean that physically makes sense. When you're talking about frequency, what you really mean is cycles per second. There's a duration there. There's a number of cycles that are involved there. And what are those cycles? The cycles are with reference to the periodicity of the wave. So even when you're talking about the particle energies themselves, you can't isolate it as something separate from the wave itself. Like you're talking about the energy that's associated with the wave, like the energy that's imparted by this wave slapping into something, you know? But anyways, I hope you enjoyed this video. This is probably like the 4th or 5th time I've had to make this video. Everyone decided they were going to be blaring music and crap in my neighborhood at the exact moment I was trying to make it. But anyways, thanks for watching. See you again.